Andrea Borghese, right?
Yes.
And he's going to talk about the geometric bond on the
Okay, many thanks for inviting me and giving me the possibility to present this work. I have been doing with my advisor, Diederik Roest, and Yvonne Zavala. So I will start from the most abused picture of the conference, probably, or maybe not. So this is supposed to be the history of our universe. And I will focus mainly on the first stages of this history. And these stages are supposed to be described by inflation. This is a theory who was proposed in the 80s to solve some problems, the flatness problems and the horizon problem. And they solve these problems, of course, but they also give us some bonuses. So the quantum fluctuation of the field called inflaton provides us with the first seeds of large-scale structure, and so they explain, in some sense, the later part of the history of the universe. So this is the easiest model one could cook up to describe inflation. And the two graphs are just two realizations of this inflation. And if one tunes the scalar potential appearing in this Lagrangian, essentially he can get predictions which are so far perfectly consistent with the observation. So the simplest model, a scalar field coupled with gravity, give us already correct predictions for the observation. Nevertheless, it's worth to ask the simple question whether it's possible to embed inflation in a UV complete theory. So in trying to answer this question, I will follow a bottom-stop approach in some sense, in the sense that I will just focus on the four-dimensional Lagrangian, so on the four-dimensional effective field theory, and I will ask the following question. So there are some Lagrangians that can describe an inflationary process, but of course there are some other Lagrangians which are really interesting, which are the supergravity Lagrangians. And I will try to see whether there is the possibility of an overlapping of these two sectors, without thinking to the fact that supergravity could be related to string theory, so via compactifications or other stories. So in some sense, this is an effective field theory approach, but supergravity can be seen as a bridge connecting the effective field theory, so your favorite model of inflation, to UV complete theory like string theory. And that's what we did in the paper, but there are some problems because we are dealing with supergravity spectra. So in a supergravity spectrum, usually you have a lot of scalar fields. For instance, in n equals 8, you have 70 scalar fields in 4 dimensions, as Adolfo told. And furthermore, during the inflation, we know that supersymmetry is completely broken because we are in an approximately de Sitter space-time. And whenever supersymmetry is broken, we know that there is the possibility of developing some instabilities in the scalar spectrum. And this is beautifully sketched in the fact that, for instance, in n equals 4 and 8, so half maximal and maximal supergravity, nobody has been able yet to find a stable de Sitter vacua. And a stable de Sitter vacua, in some sense, is related to the almost stable phase of inflation. So what's the situation we want to realize is illustrated by this cartoon. The best situation we would like to realize is to get in supergravity one scalar field which has a mass below the Hubble scale and a bunch of other scalars, all the other scalars, which are above the Hubble scale and are decoupled from the inflaton and from the inflationary evolution. So this is what we were trying to to constraints, looking at particular supergravity theories. And this is really difficult, as I said, because there are instabilities popping up everywhere. But there is good news. And the good news is that in supergravity, the scalar dynamic is tightly constrained. So in particular, all the scalar fields arrange themselves in coset. And this coset can be, well, in manifold. And these manifolds can be coset manifolds for extended supergravity or complex manifold of special type, like Hodge Kähler or special Kähler, quaternionic Kähler, in the less supersymmetric theories. And as they arrange in manifold, we can ask ourselves whether there are particular directions on this coset or on this manifold that are singled out somehow, that we can study always. And this is what we did in the paper, essentially. We took as particular directions on the manifolds the Sgolstini direction, which are just the superpartner of the Golstino fields, which are essentially the Goldstone boson of supersymmetry. When supersymmetry is broken by the super Higgs mechanism, you have these Goldstone modes, which are spin 1/2. And then when you take a supersymmetry transformation, you arrive to the scalar sector, and you single out always for every supergravity theory, whenever supersymmetry is broken, you single out these directions, which are called Sgolstino direction. So depending on the amount of supersymmetry, you can have one complex direction up to 64 complex directions, and then these complex directions become real because there are some special duality relations between scalars in n equals 8. So essentially, they are always there, and they can be pinpoint analytically, these directions. They have been used already some years ago to check perturbative stability of critical points. So whenever you solve equations of motion, you can check whether these directions are stable. And it's good to check them because they are essentially the most dangerous, even if this statement is not completely correct. But they are unstable, they have a high probability of being unstable. But what we did in the paper was just relaxing this statement, so relaxing the equations of motion, going off shell in order to describe inflation. And we derived a bound related to these particular directions in the context of n equals 1 supergravity with only chiral multiplets. So this is usually called F-term supergravity, F-term inflation. So the theory is completely specified by the Kähler potential and the superpotential, and the Sgolstino directions are given by this projection, where alpha is a collective index on the chiral fields. Yes. That's the scalar potential. And we took an average over the two Sgolstino masses. So we projected the mass matrix coming from this scalar potential with those directions, and we took the average over these two masses. Now, this is the key point, because we took the average of two scalar degrees of freedom. And being the mass of two scalar degrees of freedom, we can get a bound which is related to the fact that in the game, the characters are 2 and not 1. So there is not one inflaton, but two scalars which plays the game, whenever this M Sgolstino is, for instance, of order 0. So we derived this bound projecting the mass matrix with these directions, and in the bound there appear some special quantities, all the quantities related to the inflationary dynamics. So for instance, epsilon is the Hubble parameter. Gamma is a parameter which tells you whether the gravitino mass is bigger or smaller than the Hubble scale, which is proportional, is the square of the scalar potential. And R twiddle is a geometric quantity which is called sectional curvature. It's just a particular contraction of the Riemann tensor on the scalar manifold, and the particular contraction is taken along this Gostino direction. And then all these quantities are arranged in the bound I presented. So as we can see, the bound contains not only inflationary parameter, but also geometric parameter. And this is really something beautiful of supergravity. Geometry is tightly entangled with the dynamics of the scalars. So for instance, the game we can play is the following. We took, for instance, this is just for simplicity, but it's valid for any value of gamma. Taking the gamma goes to infinity limit, we get this beautiful bound. And then the game we played was the following. For instance, assume single field inflation, which, as I told you, implies eta's Gostino to be larger than 1/2. Otherwise, there is at least one of the scalar fields which is below the otherwise both the scalar fields are below the Hubble mass. So let's impose single field inflation as low roll inflation, which implies epsilon less than 1. Then this bound automatically implies that R twiddle must be less or equal to -1/2. So R twiddle in particular is different from 0. And whenever R twiddle is different from 0, we have non-canonical kinetic terms in the scalar Lagrangian. And non-canonical kinetic terms in particular cases can be related to large field inflation. So for instance, whenever this Gostino is somehow aligned to the inflaton field, then you have that the inflationary dynamic must be of a large field type. Or for instance, with the same bound, we could play a different game. So for instance, impose slow roll inflation and canonical kinetic term, we see at first sight that eta is of order 0, and then we must describe inflation in a multi-field approach. So at least 2 fields are smaller than the Hubble radius. So this is essentially what I wanted to say. Just another small comment on the fact that being just related to these analytic directions, which can be singled out in any supergravity theory whenever supersymmetry is broken, we are now trying to extend this bound to all the supergravities in d equals 4. And this is work in progress, but essentially a similar bound can be obtained where the dependence on the epsilon parameter is the same in both n equals 2 and n equals 8 supergravity. And this brings me to the conclusion. So what I showed you is that geometry is tightly entangled with the dynamics of the scalar fields in supergravity whenever we describe inflation in supergravity. We can take this Gostino and derive a bound on the inflationary dynamics, which is really simple and beautiful to be analyzed. And now we are trying to obtain some similar bound in the case of next to minimal and maximal supergravity. And that's all. Thanks.
Have you explored the effect of having vector multiplets in n equals 2? Just to see whether this bound, because of these stable de Sitter solutions?
No, not yet. Because with n equals 2, well, with vector multiplets in n equals 2, the things mess up completely. So already from the vacuum stability point of view, in n equals 2 there is a theorem which states that there are no stable de Sitter vacua with only hypermultiplets. But whenever you start adding vector multiplets, then it's a disaster. So nobody has been able to prove any statement, even at the vacuum level.
So the only metastable de Sitter example in n equals 2 is with vacuum.
Yeah. So okay, you could take this as a as a hint of the fact that such a bound is a bit difficult to obtain. Yeah, but it was also special theory, so maybe you could say something about abelian gauging.
I had a quick question, but just to check that I understand which way these bounds go, because so the bound that you found was an upper bound on eta,
Yes.
and then from single field you had a lower bound which was 1/2.
Yes.
Can you explain why the lower? Because the upper bound wouldn't be a problem, or I mean, it's
So, well, maybe it's so Ita's Agostino. It's more easy to go back to this. So, this is essentially Ita's Agostino is the sum over two masses divided by the Hubble mass. So, whenever there is at least one of these, which is at the Hubble level, so if we want just one of them to be the inflaton and the other one to be at the Hubble level, then eta must be of order 1/2. So if eta is of order 0, it means that both are below the Hubble level, and so both are entangled during the inflationary dynamics. No, so there is a, of course. Yeah. So you have to use multi-field techniques in that case. This is the statement. So if eta is of order 0, then you have multi-field. Yeah, maybe it's not completely clear.
I see. So this eta is actually not the eta that I should be, not the inflaton eta that I should be worrying about, because it's a 5-5-5.
Yeah, but
You add its partner, and the partner has a logical. Okay. Let's thank Andrea.